This video is going to be about histone modifications, a part of a new up-and-coming branch of science called epigenetics, which is the study of altering gene expression without actually affecting the DNA itself. Alright, let's get down to business. Throughout your high school biology career, you probably learned all about your A's, G's, T's, and C's, and how they're all wrapped around these little beads called histones. And that's about it. Poor histones never get mentioned again. But wait, there's more to histones than meets the eye in a high school biology book. See, histones are made of an octamer of 4 core histone proteins, arranged kind of like this, 2 of each. H2A, H2B, H3, and H4, with the DNA wrapping around them. Where's H1 though? Oh, there it is. H1 isn't technically a core histone, it's a linear histone. It's found alone a little bit down the DNA and helps stabilize the DNA. But most of the fun epigenetic stuff happens to the core histones, so we'll be referring to them for the rest of the video. These histone proteins are positively charged, and DNA is negatively charged. This causes an electrostatic attraction between the two, which is why DNA can wrap so tightly around histones. Each of these histone proteins has a little tail that sticks out called an N-terminus tail. These are the areas where the histone modifications typically occur. Histones are modified through the addition of different chemical groups to different amino acids on these tails. Although there are others, the most common are acetylation, phosphorylation, and methylation. Histone acetylation usually acts on the positively charged histone residues on the N-terminus tail. Acetylation neutralizes the positive charge of the histone, thereby decreasing the attraction between it and the DNA. This loosens DNA's grip on the histone, leaving it open for enzymes involved in transcription to express that DNA. This loose, transcriptionally active DNA is called euchromatin. Histone phosphorylation does the opposite of acetylation. It tightens the DNA's grip on the histone, packing the chromatin in. It packs it so tightly, actually, that the enzymes needed for DNA transcription can't even squeeze in there and do their thing, making the DNA transcriptionally inactive. So those genes are turned off and can't be expressed. This type of transcriptionally inactive DNA is called heterochromatin. Histone methylation isn't as straightforward as other modifications. The effect it has, whether it loosens or tightens the DNA, depends on how many methyl groups are added and to which residues. These histone modifications and epigenetics in general have a much bigger impact than previously thought before, answering questions like, how do cells age? And what is a new technique that we can use to try and cure cancer? This topic has huge implications for the future, so I'm glad you sat down and learned a little about it with me today. Thank you!